Oh, a lot of people. Okay. So that's good. I'm going to give a brief. So can anyone tell me what SQL is? Someone who has worked with it.
Structured query language.
Right.
Did you say structured was us? Structured.
Structured query language.
So you can only make queries with it?
It lets you access and manipulate databases.
Yep. So what kind of databases? Anyone can answer.
You can query, you can make queries against databases, you can retrieve databases, you can insert records, update records, delete records.
Right. Okay. So what kind of databases does
Relational?
yes. So can you tell me, so what's a relational database? And maybe if you know of another kind.
A relational database. Oh. It's a relational database. It's like it stores database objects called tables.
Right. Yep.
And it's a collection of related data entries and consists of columns and rows.
Yep. And is there another kind of non-relational database? So you don't have to keep answering though.
Okay.
MongoDB.
Yeah. So
They're called NoSQL databases.
Yeah. So there are a few different kinds of databases. One is we'll learn kind of like the classic relational database, but there are others as well that we're not really going to focus on. But there are basically databases that are kind of like so MongoDB uses files essentially, so it's like a document database. There are NoSQL databases, which are basically like giant objects. So they don't require, so it's like having a giant object or JSON object or something like that. So if you want to store data and you don't necessarily want to enforce a particular structure on your data, you can use that. So it can be very flexible. There are, benefits and drawbacks to using one versus the other, of course. But we're going to focus on SQL and relational databases. So here's a representation of a relational database. We'll talk more about what this is actually doing and what it means. And a non-relational database, this could be represented in different ways, but something like a JSON object. You have a deeply embedded JSON object, and there's no requirement for the structure here. So you could have a game here. You could have something else. You don't have to have a certain number of players. A player might have an ID, or it might have some other properties. So there could be a lot of variation within whatever you're storing there. A relational database imposes a much stricter structure, which obviously could be good or bad depending on what you're doing. And here, this is kind of like a version of UML. So we've talked a little bit about UML, but instead of classes,
Chad, just to confirm,
yeah.
Are you sharing your screen? Or
Yes.
should
Oh,
you be?
I should be. Am I not? Okay. Sorry. Thank you for asking. Okay. You guys can see my screen now. So the relational database and the non-relational database. I'm sure this makes at least a little bit more sense now. So again, this is kind of like UML, So these are, instead of being classes, right? We kind of mocked up or reverse engineered a program, right? Or even designing a program from scratch. You can use UML to do that. So here we have table. So the unit of a database is going to be a table. So these are all different tables, and each table has so these are columns, although it's represented, horizontally, which is a little disorienting. This is like a column. If you imagine a spreadsheet, this is like you have a name and then a price column. And here's the product table, and it has these has a product ID. So it's like an ID, has a name and a price. And each table has its own columns, and then rows will be like, creating instances. You can have lots of different customers. You can have lots of different products with different names and different prices. But these tables, you can have a database with just a single table, but typically where you really start seeing the benefit from a relational database is when you have multiple tables that are connected to each other. So we don't have to worry, we don't have to go into detail here, but this notation, this single line here means one, and this little crow's foot with 3 means many. So a product can have many order lines, and an order line can only have one product. A customer can have many orders, and an order can only belong to one customer. So we have these different, again, you don't need to worry about those details right now, but just to show you that the basic things that we care about when we talk about database design are the basic unit is going to be a table. Tables have columns, and then tables also have relationships to other tables. Okay, so we have this storage mechanism. This is basically the structure of your database: tables, columns, and rows, and then how you not just query, but how you can modify your tables. So here is a representation of a table. You can think of it as a spreadsheet, something like that. So we have an ID. We have a first name, last name, and then on probation. So this is the table, the whole thing. And this is a column, right? So there's an ID column, first name column, last name column, etc. And then a row. There are, you will likely encounter, if you are reading up on the stuff on your own, different terminology for some of this stuff. Sometimes a row is called a tuple. That's actually where the Python data structure comes from. Okay, so we talk about designing a database. We talk about schemas. So if you have an application, right? I want to design an application. It needs to persist data. The basic units, again, as we've already said, you're going to have tables, columns, tables and columns, basically. And one of the perks of using relational databases is that you can enforce, again, you can be fairly strict with the kinds of, you can be very specific about what you accept as a valid entry. So just like in Python, we have types, although Python doesn't really enforce it. So maybe if you think of a different language like Java, if you have an int type, you can't just willy-nilly give it a float or a string. So with SQL databases, you can specify the type of value, and there are a whole bunch of different types. So there's characters, there's strings, and there's actually different kinds of strings. Then you can specify, what is the maximum number of characters in a string. There are basically floats. You can have decimals, you can have integers, you can have dates, different kinds of dates. And depending on which implementation of SQL you're using, you might, at the edges, there's some variation. I should also mention quickly that SQL is kind of a, it's a general standard, and there are lots of different implementations, but the implementations are 99% the same from a user perspective. If you write a query for MySQL, it'll work on Postgres almost all the time, with extremely rare exceptions. So for this course, we're going to be using PostgreSQL, but if you're looking up how to make a query, you don't need to just specifically search for Postgres. Okay, so yeah, again, not only can you determine what kinds of values are acceptable, you can also make sure it's null or not null. So if you want to create, if we go back to this example right here, so we want to add a new student to our database, but we don't have a last name. Well, you can decide, does my application need to have a last name or not? And if it needs to have a last name, you can make this requirement. You can add a not null qualification, or if it is, if you can handle a blank there, then you can accept it. You can also accept it and then add a default value. So, okay, so SQL is a, I won't argue about whether it's a full language or not, in part because I don't know, but I guess that shouldn't stop me from arguing about it. So you can do some very complex things with SQL. You can actually write functions, and you can have conditions and stuff like that. But for the most part, what you're doing is you can create tables, and then you can basically determine the schema for those tables, like what columns they have and what values those columns have. And then you can also input data using SQL. So I can create a bunch of rows. I can add new students to my student table. And then you can also delete data, and then you can run queries. So here there are, people have different preferences for should use plural or singular for table names. So you'll see people preferring one or the other. So here's just example of how you create a table that has that table that we just saw. So we have this. We have some keywords. We have create, table, and then students is just whatever you want to call the table. So notice that these are all in angry case, I guess. But SQL actually doesn't care. So this is a convention from in the days before our very nice color-coded code editors and stuff like that. So the standard is to have keywords be all caps, but if you use all lowercase, it'll work just fine. But it's just more of a convention. So we're creating a students table, and we're saying we're going to describe all of the columns. So it should have a column that's ID, and that's going to be an integer. Then we have a first name column, and that's going to be something called varchar. So varchar, and then we specify the maximum number of characters. I think 255 is the max for this particular data type. So if you have varchar of 10 and someone tries to create a new entry in your database with 12 characters, it'll be rejected. They also have Boolean, so that's familiar to us. There's a whole bunch of other, it's like a dozen or more different types. Okay. Yeah, these are just some common column types that you'll see: integers, decimals, text, dates, timestamps. So once you create a database, especially if you're using it in an application and starts going into production, you generally ideally you won't have to change your database, but likely you will. But you can do that. Doing it in production is a different story, but doing it before you get to that point is fairly easy. You just run different commands. So if I decide that in fact, I want to restrict first names to be 100 characters, you can just run another SQL command, and that will update the schema. Okay, so a lot of the same basic principles that we've learned elsewhere in programming apply to SQL and to designing schemas. One is the big kind of issue is redundancy, or keeping things dry. So it's very easy to start repeating yourself, and you have multiple copies of the same data, and then you can create all kinds of problems. So we'll run through an example of that in a bit. But here's from the slides. So we have a database now. We have our students, right? First name, last name, on probation. And now we want to add some address information. So this is okay, and it works. But there are a few problems with this. One is that we seem to have kind of two different kinds of information here. So we're storing, so of course this is all related to a student, but maybe things like the first name and last name, argue maybe even on probation, this could be a part of some other category maybe. And then we have this address. So we've got all these different kinds of information all in one place. So we can split that up into another table. So this is the great thing about relational databases, is you can have lots of different tables, then you just make sure that they are connected properly. So we pull out all of the information for students, and then we have all the information for addresses. But of course, we need to know which student lives at which address. So in the address table, we need to have student information, right? Otherwise, we just have kind of random addresses floating around and then random students floating around. So there's no way to connect them, right? But of course, we're repeating ourselves, and this is bad for a couple reasons. So why might this be a bad idea?
I was going to say, when you update one of those students in students, then it's not going to be updated in addresses.
Yeah, you lose or you risk your data's integrity. Right? You have multiple copies of the same data, and some of it's getting updated and some of it isn't. And then what's the real state of your application? Yeah, so that's probably the biggest one. Also, of course, excess memory usage, depending on the scale that you're operating at, that might be important. So we fix this by using, this is called a foreign key. So notice here that we have our students, we have ID. And ID should be unique. So every single row here should have its own ID. So people could have, maybe multiple people could have the same first name, and that's fine. But we want IDs to be unique. And again, that uniqueness constraint is something you can impose on a column. So we could have first names be unique if we wanted to. We could enforce that on our database. But this is what's called the primary key. And there are different ways of getting a primary key. Sometimes primary key will come from some piece of data that's kind of organically in the data set. So if you have an email, for example, presumably you're not going to have two different people with the same email. So that's probably something that will be uniquely identify them. You can also use combinations of other keys, which are called natural keys, data that's already kind of in there. But we will basically always be creating a synthetic key. So we'll use some Postgres magic. We'll just tell Postgres to basically create a unique primary key for every entry. So we don't have to worry about it. Okay. And then, so we have students. Now we have IDs. We have addresses. They have their own IDs. And then all we have to do is associate a given address ID with a given student. So if Tiana lives at address ID 4, then we just look up where's address ID 4 in the addresses table, and we can get that. So we're not, I mean, technically we are doing some duplication because we have to have the keys in both, but we're, if Tiana moves, all we do is change one thing here, right? So if she moves to this address, or if she moves a new address, we create a new entry, but we don't have duplicated data floating around. Okay, so here's an example. Yeah, is there a question?
Oh, yeah, I was just going to ask if there was any preference in, say, if someone wanted to say that the first address there of ID 4 have a column that says it's linked to student ID 1 instead of having student ID 1 saying that it's linked to address ID 4. Is there any like?
I don't think it makes it. So that's a good question. I don't think it makes any difference in terms of like performance. I think it's just how you understand, like from a human perspective, how you understand. So if the primary thing we care about maybe is students rather than addresses, then students will kind of own the address.
Okay,
and
thanks.
So it also depends on the kind of relationship. So there's a one-to-many here. So we could have it when it's designed like this, we could have lots of students living at the same address. So if you have like a brother and sister going to the same school, they could both live at the same address.
What about if someone had more than one address?
Yeah, so you can do that. You can express. So we're not going to go into like relationships right now. We'll on Saturday we'll talk more. We'll stick with more basic things, but yeah. So you can have a many-to-many relationship potentially. So a student could have multiple addresses potentially. So there are edge cases and design choices, and that all will come into play. So you could model that where a student has multiple addresses. But yeah, I don't want to get too into it, but you can't directly model that in a database. You have to use a third table. You have to use a join table. But we'll talk about that later. Yeah, so here's just an example where someone has signed up, for example, someone has signed up, two people signed up with the same address. That's a bad idea. Okay, so queries. So the basic thing you want to use is select. So select will be the keyword. You'll select something, select columns basically from the table. So we'll see more of this, but select, insert, update, and delete. You can perform all of those operations. And you'll see when we get to web application, making full stack web applications, there's an acronym called CRUD, which is kind of unpleasant sounding, but it's create, read, update, and destroy. So you can write a web application that performs all of those basic database operations. So select query. So select. Would anyone like to take a guess at what this query does?
Retrieve all the information in students.
Yep. Yeah. So it'll retrieve all of it. So this slot right here is actually the columns. So it's going to retrieve basically the data from all of the columns from the students table. So if instead of select star from students, we did select first name from students, then we would only get this column. Okay, and you can specify more than one column. So again, you can use star, wildcard to get all of them. Probably not something you would want to use in production really, depending, if you have a very large database, queries can take, some time to come in. So generally speaking, you want to be specific, but for testing and kind of local development purposes, the star, select star is your friend. So select ID first name. So if we want the ID first name, you can also change column names. You can have much more complicated queries. We'll see a little bit of that in the coming days. You can also add more specific information. So instead of just saying, hey, I want to grab all the information from the first name column right here, I just want to grab the information from the ID column and the first name column for rows where the ID is 2. So you can add you can make this query more restrictive by adding a where clause. So this is basically like a conditional. So where ID equals 2. So only rows where the ID is 2.
And Chad,
Yep.
is it returning just the data that's in those 2 columns, or is it returning like a column object? Is there such a thing as that?
Yeah. So yeah, you won't directly be. So we're gonna do SQL now, and you'll kind of get you'll get the nitty gritty SQL. But by the time we actually start using this in applications, we're going to use an intermediary. We're not going to be directly interacting with SQL. We'll use a wrapper in Python, something called an ORM, object relational mapper. So for now, you can just think of this as like terminal output. You wouldn't be able to like use this directly in an application. Okay, so where one kind of thing is that a single equals can be used for comparison. Though in Python or JavaScript, you have to use double equals to do a comparison. In SQL, so single quote is also not equal. That should be familiar. these less than, greater than, that's also familiar. Between, that's kind of handy. In, again, you can, just like Python, you could create a data structure and test if it's one of multiple values. Like is kind of like a regular expression. So you can test like partial matches on a string. Here's some examples. So select everything, select select the values from all of the columns from students, where the first name, this is whatever value in this column. So first name is a column name, where first name is Andre. Notice the single quotes here as well, and the semicolon. So JavaScript, not picky about semicolons, except in a couple cases, but SQL is. So you have to include a semicolon at the end of your statement. And there's a difference between single and double quotes. So select star, and then, so this is just an alternative to not equal. And between, so between 3 and 4. So that's nice, easy syntax. Then we have this in. And so basically it's either A or B. And then we're using like. And this parentheses is basically saying the word starts with art and then some other stuff. So if the word starts with art, so, you know, art history or artistic or arts, or all that would match.
Do you know if between includes, like in this case, the 3 and the 4, or is it just like 3.0001 to 3.9?
Off the top of my head, I don't know if it's inclusive or not. Just have to check the documentation. Does anyone happen to know if the between is inclusive? I'll check that. I'll check that later. We have inserting. So we can create tables with the create table, and then whatever the name is, we can query stuff. But to actually get data into the table, so you create a table, and then you can put stuff into it, and then you can make queries. So insert, this is the keyword, insert into, and then the table name. And then here in this first set of parentheses is, these are all the column names. So first name, last name, birth date. And then we have values and another set of parentheses. And then these kind of need to line up. So Michelle would be the first name, DuPont would be the last name, and then this is the birthday. That's just a side note. The only thing that matters is the semicolon. So, you know, you can put all this stuff onto new lines and it'll work just fine. So insert into table name, all the columns, values, and then the actual entries. So don't worry about memorizing all this right now. It's just exposure. So update, so you can create stuff. You can also update. So if you want to, you know, change your email address or whatever in an application, you can run an update query. So update addresses, this is the table, and then set. So you have to be very careful. So again, I'll say SQL can be very dangerous. It'll allow you to do anything. You can, you know, delete everything, and it's more than happy to do that. So like a lot of the command line stuff on Linux, it'll let you destroy everything. So you have to be careful. And this is one of those cases where you need to specify. So if I do update addresses set line 1, this is the column, equal to this value, and then this other column equal to this value. If I just stop there after this line and run the query, it's going to update every single, it's going to update both of these columns for every single row in this table. So in order to prevent that happening, presumably you wouldn't want that to happen, although it might be a use case, you need to specify it. So use a where clause. So just like you can use where in a query, you can also use it in an update.
Is there any kind of undo?
Not really. I mean, yeah. Databases and serious applications will have copies. There are, I mean, there are, I wouldn't say it's an undo, what is it called? Transaction. So one of the other benefits of relational databases is that you can package things up into transactions. So if any parts of an operation fails, then the whole thing will get reverted. But as far, I mean, I'm not a database admin or anything like that. But as far as I know, there's no obvious way to undo an operation like that. Has anyone else had that experience? If you talk to other developers, you will inevitably come across lots of stories of people accidentally deleting lots of things that they shouldn't have deleted. So
Yeah, definitely deleted some things by accident.
yeah, if only there was an undo.
Yeah, I've done the update thing you talked about. And I think I've worked with Oracle relational, like the management system for Oracle and Microsoft. And I think Oracle has like a commit. So like after you do like an update or whatever, you have to commit what you did or else it's not actually applied to the database.
Okay.
So I don't know if Postgres is like that, but it's a nice fallback.
Yeah, I think I think you can change the settings on Post. I think committing is basically like an auto commit. Although when it comes, we'll see some of the wrappers that we can use Python. So you do have to explicitly commit in order to, you know, save an operation. But when you're just running it as raw SQL, okay, so delete, same thing. So again, if you're deleting, you want to make sure that you're adding a where clause. So you are specifying, not deleting everything. There you go. Okay. So sorry, this went on a little longer. I just want to do a quick, man, it's already almost 8 o'clock. All right, let me try to do this quickly. So here we have, let's say, like our database, right? So here's the database: name, address, age, birthday, order item number, order item cost, order total. And we have 2 customers. We have Bob and Sally. Bob hasn't made an order yet. Maybe he's like signed up for the service, but he hasn't actually made an order. Sally has made an order. Does anyone see any obvious problems with the way our database is set up right now?
You can't make a second order?
She could. So let's try. Just get one of those and we'll add a 0.
Age doesn't change as your as the years get older, and if you update things, you have to update it in every single address line.
Okay,
And-
so let's talk about this age birthday. So what's the problem with this?
It's redundant information.
Yeah, so we can figure out what someone's age is based on their birthday, right? So we don't really need to be storing this information in the database. We have a similar problem with order total. If again, if the number of things you order times the cost, if this is a constant, for example, in a simplified case, then this order total again is redundant because we can derive this information from these two columns. So there's something when you're kind of going through this process of figuring out how to design your database, there's these things called normal forms, and it can get very academic. But if you're interested, you can look up normal forms. It's like 6 normal forms or something like that. But the basic idea behind the normal form is that you eliminate redundancy like this. So if a piece of information is derivable from some other piece of information that you already have, then you can get rid of it. So another issue is that when Sally Smith, so let's imagine, again, let's try to imagine this at scale. So we have 10 million users, and only 10% of them have ever placed an order. Well, so now we have millions and millions and millions of nulls, right? So maybe that ends up being expensive. That might cost us money in terms of storage. It just might make everything inefficient. And also why, right? So we've coupled these two different things into one row. We have order information and we have this user information. Arguably, this could also be separate. So we should probably be pulling things out into different columns. So another issue is the address, right? So this is multiple pieces of information, right? This is like a street number, a street, a city, and a state. So typically, you want something. You want information in one of these slots to be atomic. So you want it to just be one piece of information rather than kind of a list of a whole bunch of pieces of information. So this would be a candidate for either breaking up into multiple columns here or creating a new table. So the other problem is that every time we create a new order, we're duplicating all of this information. So how we would solve this is we would end up creating several tables. We probably have an address table, maybe like a user table. You can have an order table, probably maybe a product table. Am I cutting out?
A little bit.
Okay. But so we'll talk about this more on Saturday, how we can design schema. But this is just kind of a general exposure and overview. Let's go ahead and let's look at how we can actually do some of this stuff on our machines. So we should have Postgres already installed. So if you run psql, if you run that command, if nothing blows up, you're probably good. So you're basically inside a kind of a REPL for your database. So by default, it'll it'll create a database based on your username. So I'm going to quit out of this. So quitting is /q, \q. Now return me to my terminal. So I'm going to create a database here. So the command for that is create DB and then whatever you want to call. So I'm just going to call mine test. Okay, so I just created, again, I ran a command and nothing happened, so that means it worked. So let's see what's in test. So I'm going to go PSQL and then the name of the database. So PSQL test. And whenever I share my screen, I don't know what, it's like messes up my display. There we go. So now I'm here, but I'm inside my test database. So I've created a database and now I can interact with it. So if I want to describe what's in this database, I use \D for describe. And I don't have any relations. So a relation basically means table. So I don't have any tables. So I've created a database, but I haven't created any tables. So we can, of course, create tables. So let's try running create. I'll use all caps for a little while, and then I'll get lazy very quickly. Table. We'll call it first table. And let's see. We'll have an ID. That's a good practice. And that will be serial. So serial is kind of like a built-in thing. So basically we're telling Postgres, hey, you take care of it. And then let's get a username. And username will be a varchar, let's say up to 50 characters. So I add a semicolon at the end. Okay, so I add a semicolon at the end, and then my output is create table, which means that it worked. So now if I describe my tables /D, I can see that I have, so I'm running describe /D in my database, so I can get all of the tables. So I have this table, which I'm calling first table. So I can run describe on the table that I've just created. So /D first table, and it will allow me to see everything that I've added to that. So I have an ID column, which is of the type integer, which is what it's basically just giving me an auto incrementing integer. We use the serial, and then character varying 50. And you can see that that's exactly what we told it to do. So we've created a table here, so we can actually add some entries. So let's do some insert statements. So insert into first table, and we need to say, so the ID will be taken care of, so username. And so this is the column, the table, the column, and then what we actually want to put in there. So use single quotes. And if I forget the semicolon, which you and I will do very frequently, it'll just kind of go to the next line. And you'll wonder what happened. Why isn't this in my database? But it's basically just continuing. So it's kind of in a suspended state right now. You can just add a semicolon on the next line, and then it will execute. So now I have some kind of value. I have something in my database, right? But how do I know? Well, we can run a query on the data that we just added. You can do that with select. So you can do select, and I'll use star just to get everything, although there's only one column basically. So select star from then the table name, first table, and add my semicolon, and I see I get back Bob. So I'm going to add one more entry just so this is slightly more interesting. Okay, so I'll do insert into first table, and username, values, I'm going to add my semicolon here. I've inserted it, so now I'll run a query, select star from table name. First table. And we see we get both in there. So let's say we only want to get, we only want Jane right now. So there's a couple ways we could specify, since both of these values are unique. Let's try making a query by ID. So we'll do select star. Well, actually, let's just get the username. So select username. We're going to specify the column rather than just using star. So select the username from first table. First table where, and then we want the ID is 2, and we just get Jane. Okay, so I'm going to go ahead and drop this table. So drop table, first table. The table is dropped. So if I try to run that query that I just ran, it doesn't work. I get an error. Relation first table does not exist because I deleted it. So now I'm going to quit /q, and I'm going to just drop the database. So drop from my terminal. So drop db test, and so that is all gone now. You can also so we'll do this. So you can also use script. So you don't have to do everything by hand on the command line. You can also just run a script. So we'll get rid of this. So again, here I'm being lazy and I'm not uppercasing, but it'll work just fine. So this first line, as you're developing, this is probably a good thing to have. So we'll leave this off for now. Comments, by the way, 2 dashes. So I'm going to create a database, create DB and I'll create test. Yeah, let's call it test. And then I want to basically run this file kind of as a script in my test database I just created. So I can go PSQL, and I specify the database test, and then I can use a flag -f for file and pass in that file, test SQL, can run that, and I get some output, created a table, did some inserts. So let's check out what we got. So PSQL test, we're going to go in there and look around. So describe, and we have this table, first table. So let's describe the table. We can see that we have a username and the price. So this is an integer, this is a varchar. Okay. So now I can run a query on it. So I just want to see everything that's there at first. So select star from first table. And I get all these entries. Okay, so I can do something like get all of the names. All right, so someone help me do this. So I want to get all of the names of the rows where the price is less than 5.
So select uname from first table where price less than symbol and 5.
Okay, and we get a semicolon.
Semicolon, yeah.
Good, so that works. So now we have just these. What if we wanted the price and the name?
The same as the previous, but just add comma price after uname.
Okay, so we can do uname, comma, price. Okay, so that works. Now we can see both of these columns. What if I don't really like uname? I want to, let's say, I want to call this user, at least during my query. So one thing we can do is uname as and notice that this is now user and not uname. Sorry, I know this is hard to read. Let me see everybody squinting.
So that's like an alias,
Yeah,
alias or alias.
yeah, it's an alias. So you can do as. So this is the original column name, and we're just saying we want to call it, like for the purposes of this query, we want to call it, we're not actually changing the name of this in our database. It's just like, you know, while this query is going. So that's, I mean, that's the basics of how, so let's see what happens. I'm gonna quit this. And what happens if I try running this script again? So I have my same database. I get an error. The error is the relation. So relation means table. So again, sometimes you get there's a lot of redundancy in the nomenclature, but a relation means table. So it says the relation first table already exists. So I'm trying to create a table right here, but I've already created that table in the database, so it won't let me do that. So as you're developing, it's usually good to include something like this, because it'll just delete everything and then start over again.
So Jay, you created that table without so you can create this table without going through the terminal?
Yes. Yeah. So so you can either put your SQL statements in, like basically run it as a script. It's just like Python, right? So
Okay.
we can have a file and we can save it and we can write a whole bunch of Python stuff in it, and then we can just run the file from the terminal. Or we can go into the REPL here and write code.
Okay.
Whatever we do, right? So it's the same thing. So you can either write it as a script in the file and then run the script, or you can go directly into the shell and do it there.
Okay, seems like it's easier to write the script and just run the file.
Yeah, for sure. I mean, it's the same thing with Python, right? You don't want to like write a program in the Python REPL. It's usually used for just, checking a quick thing or two.
So I noticed that when you ran that file again, did it insert new all those inserts again?
Let's see. So that will work. We could do I believe that's the right one. So let me try. So again, you can do very dangerous things with SQL. It won't stop you.
I think you'll need to delete the table before you create it again.
Yeah.
Oh, you have that up, yeah.
It's just my term. I don't know why it happens, but when I share my screen, it messes up. Like I can't see my commands. There we go. Let's try running this. First table. Yeah, I'll need to check. Yeah, I'd probably have to look that up real quick, but it's already 8:20, so I'll stop here. So the exercise for today